Welcome to myprojectbazaar.com.
Title of our product is a low voltage radiation hardened 13 transistor SRAM Bitcell for ultra low power space applications. Abstract of our product is continuous transistor scaling coupled with the growing demand for low voltage low power applications and increasing the susceptibility of VLSI circuits to soft errors, especially when exposed to extreme environmental conditions such as those encountered by a space applications. The most vulnerable of these circuits are memory arrays that cover large area of silicon die and often store critical data. Radiation harden of embedded memory block is commonly achieved by implementing the experimentally large bit cells or redundant array and maintaining a relative high operating voltage. However, in addition to the resulting area overhead, this often limits the minimum operating voltage of the entire system, leading to the significant power consumption. In this paper, we propose a first radiation hardened static random access memory Bitcell targeted at low voltage frequency while maintaining a high soft error robustness. The proposed 13D employs a novel dual driven separate feedback mechanism to tolerate upsets with charge of deposit as high as 500 FC at a scaled 500 mV supply voltage. This is achieved with the cell layout that is only 2 cross larger than the reference 60 lamp cell driven with the standard design rules. Now we are going to discuss about the flow diagram of our product. In our product we are using a different input and get the different output with interleaved by an NMOS and PMOS transistor. Write the word line and bit line and the input signals are directly applied into the PMOS transistor. They are directly interconnected into the NMOS transistor as well as the second input is directly applied into the NMOS transistor. This NMOS transistor coming input will be directly obtained by in the inverter. This inverter to get the final output of the Q and Q bar. The writing inputs, the writing bit line and the writing word line will be applied into the PMOS transistor and then the output of the PMOS transistor is directly applied into the NMOS transistor via some inverters. This intermediate place is denoted as an Q. This in order to get the inverse output of the Q, they are denoted as an Q bar. Using inverter to obtain the Q bar output from the Q output. We are using the input signal will be a clock pulse or signage players and etc. in the input of the NMOS and PMOS signals. There are two inputs are used. Both are depending on the same inputs. They are all the flow of our product. Now we are going to discuss about the running procedure of our product. In our product we are using a Tanner EDA 13.0 version tool. Now open the tool window to create a new schematic using the file menu to create a new design. In order to assign the design name and the desired path, assign the design name 13 SRAM. After assign the design name, click OK to continue this. After creating the new design, now add the library files using this add option. Assign the library file path in order to add the libraries. After assign the library path, click OK. In our product we are assign a 30 SRAM or a product name to create a new design using the cell option to view the new view. Okay, in order to assign the cell names, after assign the cell name we click the OK. In our product we are using as 60 SRAM and 13D SRAM. There are two cells are created. First we are going to simulate the 60 SRAM. Double click to select the 60 SRAM. Before starting simulation, first we set up the setup simulation option. General to add the library files of our tool. We are using a generic 0.25 library TTS and a transient delay, and then assign the transient and Fourier analysis to assign the stop time of our running waveform, maximum time setup and start time and print time setup. After assigning this transient and Fourier analysis, click OK. Now start run this waveform using this start simulation option. This is the output waveform of a 60 SRAM. Expand this waveform using expand chart option. VBL is on a bit line of a input, WL is on a write line, VQ is an output of our product, VQ bar is an inverse operation of a VQ. Similarly run the 13D. 13D means 13 transistor RAM. Select the 13D SRAM to start simulate this waveform. This is the output waveform of a 13 transistor SRAM. Expand this waveform using this expand chart option. This is the input of a VB, this is input of VA, this is an Q bar 2 second Q bar output, this is an Q bar first output. RBL is on a read bit line, this is on a read write line, this is on a write line, this is on a write bit line. These all are the process to obtain our product output of VQ bars. Thank you for watching this video.